Okay. Good morning, everybody. Welcome. So we're in the last week here. This is week 12 from your syllabus. I'm planning on finishing up. We're going to just go up to section 11.9 in chapter 11, and then we're not going to do the Doppler effect stuff, I don't think. And if we have some time on Thursday, we'll do some course review, or we might be also finishing up. I can sort of consider Thursday to be our last class. And then there's a break, and we come back in the winter, and Professor Harlick takes over. So she's here. Would you like to? You want to try talking in the? Okay.
I have to learn how to use it.
Yeah, there you go.
Do I just talk to it?
You just talk to the thing, yeah.
Okay. Hi everyone. For those of you who've been in this class from the beginning, you probably or may not remember me. I was introducing surveys in the beginning in like all of your classes in the beginning of the semester. So my name is Anya Harlick, and I will be taking over Physics 132. And I just want to let you know that when Professor Harlow and I designed this year, we actually talked a lot to make sure that both courses are as similar as possible in terms of assessments, pace, and everything. So there's not going to be that many, well, the content is completely different, but in terms of how the course is organized, there's not going to be that many changes to make sure that like there's enough surprises through the year. So good luck on your final, which is, if I remember correctly, on Saturday morning, like whoever designed that, horrible. And I'm looking forward to seeing everyone, January 8th, I believe it is, yes. So see you everyone January 8th, and I'll leave you to it so you don't have too much to learn on last day of classes.
Okay, thanks very much, honey. Okay. All right, so now you know who your new prof will be. This is the course evaluations that have been coming in. Thank you very much for doing those. You have till Friday to fill those out. Those are the official ones that go up to our bosses, and we'll eventually get the results. I'll be able to read it in, I think, late January. They send me your comments and things. So there's this slide. So there's also this exam jam, which is happening on Friday, December the 8th. It's got a bunch of stuff going on. I think they have free massages. They have puppies. Usually, I think there was about 3 puppies there last year. It's for like pet therapy. I think you could play with the puppies. Also, after me, I don't know if you're taking Chemistry 135, but Professor Jokish and Browning are also planning to show up there. So check it out. Exam jam. Totally optional. So I always get interesting things on the pre-class survey. Somebody asked me this morning, I heard that sound creates a small amount of heat. I wonder how long you would have to shout at soup for it to be nice and warm. So I take this as a serious question, and actually it is good to think about just how little energy is transmitted by a sound wave. So shouting at 80 decibels, if you look at your table from chapter 11, that's 10 to the minus 4 watts per meter squared. So if you're shouting at soup, and maybe it's a 10 centimeter radius bowl or something, it might be 0.03 meters squared would be the collecting area of the soup. And so if you multiply that times the intensity of the soup, and if you assume that no sound reflects off the soup, it all gets absorbed into the soup, it would absorb about 3 microjoules per second of energy. And so, and a specific heat of soup is about 4 grams per, 4 joules per gram per degree Celsius. So if you're going to warm it from like room temperature up to a good soup eating temperature of 90 degrees, it's about 70 degrees Celsius. So it's about 84,000 joules. It would take around 900 years of shouting to get the soup up to that temperature. Now, that's a minimum because that also assumes that over those 900 years that no energy is lost from the soup to its environment. It's just collecting sound energy. So anyway, you can't do it. You need a microwave oven or something like that to heat your soup. But that was a good question. Thank you for that. Okay. How's everyone doing out there? I feel like there's been a bunch of frantic stuff. Let me know if you have any questions or anything else that you feel is relevant. So this is about the principle of superposition. So basically, here's a guy on a motorcycle. Particles cannot occupy the same space with the same state. This is the Pauli exclusion principle, which is you can't have any fermions in the same exact state with the same location. So you crash. But waves are not like this. They pass right through each other. And when they do that, they interfere. If you have two distinct waves at the same place in x and in time, same place and time, then the y displacement, they call it in the textbook, is just the sum of the displacement of either of the two waves. You can sort of see these two waves passing through each other. And when they're in the same location, the dotted lines, you can kind of see what the old waves are, and the solid line is what the new wave is. So it's called the superposition principle. Y equals y1 plus y2. Y1 and y2 are the displacements of the individual waves, and y is going to be what you really get. So, and you have constructive or destructive interference, as it's called. So if y1 and y2 have the same sign, then the final amplitude of the wave will be higher than the amplitude of either individual wave. So it sounds like a bit of an oxymoron, constructive interference. I kind of think of, I don't know, in football, if you're running interference, you're trying to stop somebody. You can actually have two waves, same place, and then they create something that's greater. But you can have destructive interference if the signs are opposite, and then the final amplitude will be less than the louder of the two, or the higher intensity wave. Yip. So.
In destructive interference, like those two waves cancel each other out. Now, where does the energy go?
Well, yeah. So that's a good point. You can have two waves that totally cancel each other out if they're opposite signs. Yeah, the energy kind of disappears. And what's also interesting is that if you do constructive interference, you get double the amplitude. It turns out the intensity, or joules per second, is proportional to the square of the amplitude. So when two waves interfere, you end up with, it's this perfectly aligned, then you can get 4 times either energy. So you kind of double your energy somehow when you're doing constructive interference, and you can get 0 energy when you have destructive interference. So, but they average out to be 2. So basically, whenever you actually interfere two waves in real life, there's constructive and destructive. There's fringes, positive and negative fringes, and they all average out so that energy does get conserved. So the mistake you make when you do this is you always analyze things in one dimension, right? And you imagine some sort of infinite plane wave and another infinite plane wave that are going along, and they could destructively interfere, and all the energy could go away. But in real life, it can never happen, because you always have waves going in sort of different directions. So that's how I kind of solve that. It's a great question, though. I spend a lot of time thinking about that one. But yeah, it doesn't really seem to conserve energy, at least locally. But let's see if we can do a top hat question. These are a little different than the ones I posted, so see if you can think on your feet here. Because the one I posted is very, very similar. It's pretty much exactly one of your problem set questions on the problem set 10 on chapter 11. Let's say we've got these two shaped waves moving at 1 meter per second towards each other. So one's going at +1 and one's going at -1. And 6 seconds later, which of these A, B, C, or D should be the pattern of the resultant wave? See if you can try to figure that out, and we'll try to do it. So I found this one pretty hard to picture. So we can actually try to move this. So 1 meter per second. So 1, 2, 3, 4, 5, 6 seconds later, that's where that one will be. And then 1, 2, 3, 4, 5, 6 seconds later, that's sort of where that one will be. So what I'm kind of picturing is that the sum of these two waves is, if I can kind of draw it here, it's going to be 0 over here. Then there is no wave here, so it'll just follow this one. But then when this one goes down, this one goes up at the same rate. So I feel like when you add these two things, it'll probably be flat on the top. Makes sense. It was a hard one. But that's my basic idea. So I'd like to see. I want to see how many of you guys got that one. Nice. Okay. So that was great. I found that one to be a pretty hard one. Okay, let's do another one, maybe a little easier. These ones are going at +6 and -6, so they're approaching, two waves approaching each other. Now these are flipped, right? One is identical to the other one, but in the opposite direction, the negative y direction. One's in the positive y direction. So I think when they pass over each other and overlap, that's when you're going to get the energy will go away momentarily. I mean, another thing that I would think of is that there might be some kinetic energy in the string as it's kind of moving at that exact instant. So that's another place the energy can go. You'll see that with standing waves. But anyway, I'll give you a minute to do this one. Oh, is there no graph? Darn it. I think I may have forgotten the graph on your telephone, so sorry about that. That's my sort of reasoning there. So sorry that I didn't send the image over, but I do think at 1.6 seconds, that's when they'll overlap. And when they overlap, I think that's when the displacement everywhere would just be 0. I think that they start off with some separation. The distance here is about 19 centimeters. And so, V is V relative or something like that, d over t. So t is going to be that 19 centimeters divided by the 12. Centimeters for a second. So that's where I got it. To be thereabouts. Okay. All right, so that's your Monday morning warm-up. There was also this question. The idea here this morning, two sound speakers A and B are side by side at a distance of 100 meters away from a listener, and they vibrate in unison at 85 hertz. So frequency is 85 hertz. And the idea is that the speed of sound is equal to the lambda, the wavelength, times the frequency. So you can solve this for the wavelength, and you get V over F. So 340 meters per second is the speed of sound waves, and if you divide it by 85 hertz, then you get that the wavelength is 4 meters. So if you do the difference, x1 minus x2 is equal to half a wavelength, this will be perfect destructive interference. That's where the 2 comes from. That sound okay? That's for two sine waves. There'll be all the crests will meet troughs if there's half a wavelength in between them, if you shift them. Sound good? Okay. Moving right along, I want to talk about sound. So that was sort of a little bit about interference. Then we're going to talk about sound waves and frequency, a little bit about beats, and then I'm going to end up with a bit on standing waves. So your ears are able to detect sinusoidal sound waves. So once you have a sine wave, you have a frequency. The frequency is, if it's between about 20 hertz and 20 kilohertz or 20,000 hertz, you can hear it. And the lower frequencies are perceived as these sort of bass notes, and the higher frequencies are perceived as like high pitch or the sort of the treble notes. And if you go above 20,000 hertz, then that's what we call ultrasound. If you go below 20 hertz, that's called infrasound. And all those different pressure waves exist in the air, but our ears cannot detect it. But your ear is extremely good at detecting different frequencies within the same sound. So this is sort of the idea is that you have some sound waves that are coming in, delivering some energy. These are the sound waves. And what they do, it's the pressure waves, they oscillate the eardrum here. And then those oscillations are brought through some little bones, which have little muscles and ligaments on them, which oscillate what's called an oval window, which is touching what's called the cochlea, which inside it has this amazing thing called the basilar membrane with all these tiny little sensory hairs. And they are all connected to nerves, which go into the cochlear nerve. They all bundle up and go into your brain. And if you kind of unwind the basilar membrane and look at it, you'll see what's interesting is that it has different resonance frequencies at different positions. So if you have one incoming frequency of sound, like a pure tone or something of sound, what that will do is it'll resonate one part of your basilar membrane. And the sensory hairs there will be wiggled around, and they will transmit electrical impulses into your brain, and that'll tell your brain that you're hearing that particular frequency, or that note. So I guess we'll resonate with one part of the basilar membrane. And if you were to play at the same time two very different notes, then what that'll do is, there's a fluid pressure wave, you can have two pure tones playing at the same time, and one of them will resonate with one part of your basilar membrane, one will resonate with another part, and you will be able to pick out those two tones played together. I guess we could kind of try it. So I have to use this keyboard. It's a bit hard to do this, but if I go here and play 40, so a pure tone sounds kind of like this. And another one played at the same time. I don't know if you can kind of hear them both. That's just the higher one. Whoop. That's just the lower one, and you play them both together. It's kind of cool, right? Somehow your ear is picking out both of them, and you can kind of perceive both tones happening at the same time. Part of the magic of the inner ear. Okay. And then you have Fourier's theorem, which says that any periodic function can be made up of the sum of a whole bunch of sinusoidal waves of specific frequencies and specific amplitudes. So for example, this piano note that you see here, well, it looks like that. You can make that up with sine waves of frequency 440, 880, 1320, 1760, 220, and 2640. If you add up all those sine waves with amplitudes of these particular values, then it'll look like this, and it'll sound like a piano. And so this is sort of what you imagine that your ear is actually hearing is these different notes, but you end up hearing one particular sound that doesn't just sound like a boo, it sounds more like an actual like a piano sound. That's how we can like, for example, tell the difference between a piano and a violin. This might be the same note played on a piano and a violin, and so they have the same like fundamental frequency of 440, but they have these different, what are called harmonics, or these different sine waves that are piled on top of it, which gives it a different timbre. You can hear this sounds more like a violin, and this sounds more like a piano. So what your brain is doing is these different parts of the basilar membrane that are all working together, and you're hearing all these frequencies. It puts it together, and you get all this information. You can tell what you're listening to. Okay, so that's my little frequency. I remember last time I said we were going to talk about amplitude of sound and decibels and all that. This is the sort of the frequency part of that same. And now, what do we got left? We've got beats, and I wanted to talk about standing waves a little bit. So, beats is periodic variations in the loudness of sound due to interference. So, it occurs when two waves of similar but not exactly equal frequencies are played at the same time. And it provides a comparison of frequencies. And I'll show you. So, frequency of beats is equal to the difference of the frequencies between the frequencies of the two waves. So, we'll do a demonstration in a bit. Well, I guess we can do it right here. I can show you what it sort of sounds like by, again, going back to that room piece. See? So what if I did 220, but put the other one at like 221? So I don't think anybody can hear the difference there, right? But if you play them at the same time, that's beats. It gets louder and then softer, louder than softer. We go to 221, 222. It's twice every second. That's 223. 224. You get it, right? Okay. We got to turn that off. Okay, thanks for your thanks for your patience with that. That works all right. Anyway, you can always try that at home. It's again one of these fun things. But the way it's working with sound waves is that instead of y, like the position on an actual string, you're plotting pressure, air pressure versus time. And so when it goes up, that's when the pressure is a bit higher. That's called a compression. And when it goes down below, I guess, 1 atmosphere, then that's called a rarefaction. The pressure is a little bit lower. But when two sound waves overlap and one has a compression and one has a rarefaction, you end up with the ambient air pressure, and you don't hear a sound at all. You hear a silence. So here's two waves that are in phase. The amplitude is twice the original wave. It's going to have 4 times the intensity, actually, as Parham points out. If they're completely out of phase, what you get is just silence, I guess. The energy goes away, or you don't hear any intensity. And then if they're somewhere in between, you can get, I guess, it'll get another sine wave, same amplitude, but it'll be out of phase, but not completely. So this also definitely happens. You can have neither constructive nor destructive interference if they're not exactly like in phase or exactly out of phase. So that happens a lot too. So now bear with me. What we have is, remember that 220 hertz signal and the 221 hertz, they are almost the same. So I don't know what I've plotted here, but if this has got to be like a I don't know, 1/10 of a second or something, you'll see a lot of these oscillations. Oh, yeah, it is. It's the first 0.1 seconds. Okay. So in 0.1 seconds, you'd expect 22 full cycles of the 220 hertz. And you'd expect 22.1 of this one. So they start off completely in phase, and after 0.1 seconds, they're just a tiny little bit out of phase. I don't know if you can really see that. But this one is a little to the right of this one. So they're a little out of phase, and the amplitude, I don't know if you can see it, is kind of going down. If we plot the first half a second, then you'll get 110 oscillations in the first tone, and you'll get 110.5 oscillations of the second tone. So now, way over here at half a second, this one, the green one, is got a crest at the same place as the red one has a trough. And so they're out of phase. So this sum goes down and down and down and down until at 0.5 seconds, it goes to 0. And then it gets hard to plot after that because they end up out of phase. But then, so this is my plot, which didn't work, but it's just so many up and down wiggles that they all pile on top of each other. But you get it, right? It just looks like a solid color, but the bumps, the blue bumps, are what are called the beats. And so you get a beat at 0, a beat at 1 second, and a beat at 2 seconds. So the beat frequency is 1 every second, or it's 1 hertz, which happens to be 221 minus 220 is equal to 1. Sound good? So that's whoops, that's beats. Oh, this is a different one. So this is the first 0.5 seconds of 2 different tones that are 220 and 233. So every 13th of a second, the red curve has 16.92 oscillations and the green curve has 17.92. So that's when they go back into phase every 13th of a second. So this is a 13 hertz beat. And once again, 233 minus 220 is equal to 13. So that's where she gets this equation, 11.9, which is the absolute value of the difference in the frequencies that you're hearing will give you this beat frequency. And the idea here also is that you have to have the frequencies being pretty close to each other to hear these beats. So I don't know what you think about this. Oh, this is this morning. So I've got a top hat coming, but 2 tuning forks are played simultaneously with the same intensity. One has a frequency of 256 hertz. The other has a frequency of 252. So the frequency of the beats is going to be the absolute value of 256 minus 252, which is equal to 4 hertz. So that's where that's coming from. Piano tuning by listening. So you can actually tune a piano by if you have a frequency generator that generates a known frequency, like the right frequency, and then you listen to it at the same time as you play the piano note. You don't want to hear any beats. If you hear beats, then you know that they're a different frequency. So this is the question you should see in your phone now. If you combine the sounds of 2 pure tones, if you can imagine, at 220 hertz and 440 hertz, what would you hear? What would be the beat frequency there? So I'm kind of messing with you guys on a Monday morning. Sort of did this one. So it's the idea is that there is going to be some sort of maximum beat frequency beyond which you can't hear it. You are not going to be able to discern. I guess maybe I like B, that is the beat frequency if you just use the equation, 220 hertz. But no one's going to be able to count off 220 beats in 1 second. You'd have to count so fast. And so, and I just don't think you would at all hear it as being beats. So that's the idea there. You just hear, we did it, right? It didn't sound like whoop, whoop, whoop. So that's, sorry about that. Okay, let's do another one. Let's say you're tuning a piano and you want to make the frequency of an A key to be 440 hertz. That happens to be the frequency of, I think it's A4. It's 440 hertz. And that's how we tune pianos. It's by definition, A4 is 440. Okay, but you suspect it's out of tune. So you happen to have a reference sound source that you absolutely know is 440. And what you don't know is what the frequency of the piano key is yet, right? You think, it doesn't sound good. So let's see, when I play the 2 together, what do I hear? And you hear beats. You hear 3 beats per second. So what's the frequency now of the piano that you need to tune up? Feel free to check with your neighbor on this one. Aha, you guys. Okay, so again, this is sort of the mood that I was in. I had a deadline today for your final exam. That's what I was doing on the weekend. So, okay, Sorry, but yeah, basically what you know is that the absolute value of the difference, so whatever 440 minus, so F beat is equal to the 440 minus whatever you don't know, right? F question mark or something like that is equal to the 3. But you don't know if it's 443 or 437. Could be either. So what do? Well, what you do is, let's do another question here. A real piano tuner has to, so again, you're tuning the piano, same sort of thing, 3 beats per second. So then you tighten the little knob on the piano string so that it increases the tension in the string. That increases the speed of waves on the string. So they're going to, when you have a standing wave, it's going to go back and forth faster. So it's going to increase the frequency of the string. And when you do that, it gets even worse. You've got now 7 beats per second. So now, with all that information, what do you think is the frequency of the piano? Yeah, I think you've resolved now the discrepancy. So since you've been cranking it up and it's getting worse, you now know that you used to be at 430, whatever it was. Must have been 443, and now you're up at 447. And so now you know you're too high, and you can try to dial it back down. So this is how you have to tune the piano in practice. You have to look at the changes. Okay. All right, that's great. So, so now we want to go on to standing waves. Maybe I'll try to show you the mathematics of it first. So, I don't have the mathematics here. But basically, this is the math idea, which is that if you have 2 sine waves that are traveling in opposite directions, then when you use the principle of superposition and you add them up, you end up with this new red line function, which is called a standing wave. So what that is, I guess I'll go through the math a little bit more next class, but what you can see is that when the 2 waves are overlapping, you get a higher wave that's twice the amplitude. And then when they're out of phase, they go out of phase and in phase. When they're out of phase, the whole thing goes flat. And so I guess what we can do it in real life, and then we can try to use that simulator that I got you guys to work on the weekend. But basic idea is that this is a standing wave. You can get some particular frequency depending on the tension. I guess I can make a higher tension. If I increase the tension of this rubber hose, then I get a higher frequency standing wave. But I can also change the frequency and get what's called a different mode. So if I double this frequency, I can get this mode. So that's what's called the second harmonic. So what you can see in the middle, halfway between me and that the knot at the other end, there's a place where it doesn't move at all. That's called a node, and you can see it in the red line there. There's these positions where there's no motion of the wave. And if I try to triple the frequency from the fundamental, let's see if I can do it, I can get the third harmonic with 2 intermediate nodes. And so my hand at one side is almost like a node. So remember you were doing this with this thing. So what I have here is I'm going to shake it at a particular frequency with a very low amplitude. Oh, that's the second amplitude. So what if we go to 0.42? See that? We start. So I start this up. It's shaking it a little bit. at 4.2 hertz, and you get, it takes a little while for it to build up, but you get was pretty much the fundamental mode. But if I double that, 0.42 go up to 8.4, then I got to restart it. Double the frequency, then as these two things add, you end up with a kind of node in the middle there. So that's that sending wave. So what I imagine is that I'm sending, I guess, a sinusoidal wave along, and then it's reflecting off the end. And so you've got another reflection going from right to left. And then I guess you would even reflect off the original post. So you end up with actually multiple sine waves, but all going in opposite directions, and this is what you end up with. And you were asked, back with this morning's pre-class quiz, the answer to question 7, I think, was that you 252 hertz. So let's try it. I think I wanted all the green thingies to be nodes, right? So it turns out if you dial this up to 2.52, and then click the, it's looking kind of weird, but click restart. I mean, it doesn't quite work because, I don't know if you noticed, but the left end is not really a perfect node, right? The right end is, it's fixed, but the left end is kind of shaky a little bit, but it's much less amplitude than the anti-nodes, as they're called, so it's kind of node-ish. But you see them, all the green ones, so this is what's called the 1, 2, 3, 4, 5. This is the 6th harmonic, and it has 6 times the frequency of that 0.42 or whatever that we originally started with. So it's 6 harmonic standing wave. I don't know why I didn't bring the math for this, but I didn't. So I think I've probably done today. We do have a couple classes left after this. I'm going to come back on Wednesday, and come back again on Thursday to kind of finish things up. We're really kind of at the end, right? We're doing standing waves already, and we're not doing Doppler effect. Although I think we'll bring a Doppler football in just for good measure on Thursday. Yeah, question, yes. It's laptop.
What happened to your office hour on Thursday?
Oh, yeah, that's true. I'm going to be right here. So office hour on Thursday is canceled because I'm going to have to teach at that time. Okay. All right, see you Wednesday. Have a good one.